In today's video lecture, we are going to see about the physical memory organization, input-output addressing capability, and then the modes of operations of 8086 microprocessor. So first we will see the physical memory organization. The memory capacity that the 8086 microprocessor is capable of addressing is 1 megabyte because the address lines of 8086 is 20 bit. So 2 power 20 we will get 1 megabyte. So this 1 megabyte of memory is splitted into two banks. So one is odd bank of memory, another one is even bank of memory. So why we call it as odd bank and even bank in the sense, each and every memory location in the memory IC is represented by the hexadecimal values. Fine. So all those hexadecimal values would be an even value and an odd value. So the location that is having the odd values as an addressive value will be segregated as an odd bank memory location, and the memory locations which are addressed by the even values are separated as the even bank. So that's the concept here. So the 1 megabyte of memory here is splitted into two banks. One is odd bank, another one is even bank. So that we will see how the data will get stored in that odd and even, and how we can fetch the data from that odd and even memory banks. Fine. This is your processor 8086 microprocessor, and this is your odd bank and even bank memory. As a whole, it's a memory IC of 1 megabyte. Fine. So in odd bank of memory, your higher byte of data will get stored, and even bank of memory, your lower byte of data will be stored, because 8086 microprocessor is having 16-bit address bus. So D0 to D15. Fine. So this 16-bit data is having lower byte of D0 to D7 and higher byte of D8 to D15. So in this value, in the 16-bit value, the lower byte value will get stored in even address and higher byte value will get stored in odd address. So for example, I will say if this is our value 166A, the 6A is your lower byte and 16 is the higher byte. If we take that, if it stores in 4500 if it is the memory location, then in the memory IC, okay, so if it is 1500, the lower byte of this data, which is nothing but 6A, will be stored in even address. So then odd address 501 16 will be stored. So this is how the data will be stored in the memory address. Odd address, higher byte of data, lower address, even address, lower byte of data. So this is the procedure. This is the procedure to store the value if you want to get the value from the memory location. Fine. So we will take from the even address lower byte of data, and from the higher address, that means odd address, we will take the higher byte of data. So for example, if we take the load instruction, fine, we want to move a value from a memory location 5000 to AX register. Okay, what this instruction will do, it will move the value from the location 5000 to, so if we want to move a value from AX to the location 5000, so what will happen? So as I told you, okay, so now we have seen about storing the data into the location. If you want to take the data from the memory location, obviously we will so take this instruction as an example. Okay, so what this instruction will do, it will store the value from the memory location, store the value from the register to the memory location. Okay, so AX is a register, it will be having some data as we have taken there. Okay, so the location that we have mentioned here is 5000. Okay, so the lower byte data will stored in the even address 5006A and higher address 5001 16. Fine. Okay, so we will take, this is of storing the value inside the memory location. If you want to take the value from memory location, how will it will happen is, so we will take this instruction as an example, AX comma 6500. So what will happen now is, okay, this is even address and this is odd address. the value from the even address will be considered as the lower byte. So it will store in the register AL. So the value in the odd address is the higher byte. So this value will get stored in the AH register. Okay. So this is how the data transfer or storing the value inside the memory will takes place. So as a whole, the memory is split into two banks. One is odd bank and even bank. From the odd bank, we can take and store the higher bytes of value. From the even bank, we can take and store the lower bytes of value. Fine. Okay, next we will see about input-output addressing capability. Fine. So in the previous unit, 8085 microprocessor, we have discussed about memory and I/O interfacing. So when we are interfacing the I/O device, each and I/O device will be addressed by the 8-bit address data. Fine. Do you remember that? We have used an instruction in and out. The format will be like in, and then we have to mention the port address of the input device. So from the port address, we can know the input device and you can send the data or receive the data from that port address. So as of here, each and every address location given for the input device is also same as the 8085 microprocessor. Okay. So from in that 8085 microprocessor, we have did two techniques. We have used two techniques. One is I/O mapped I/O, another one is memory mapped I/O. In I/O mapped I/O, we have considered the input device as an input device, and we have used 8-bit port address to access the data from the input and output device. But and then in memory mapped I/O, we have considered the I/O device as a memory, and we have used 16-bit data as an address value to access the data to and from the input and output devices. That you guys will remember already. Okay. The same thing we will do here. Here each and every input and output devices are addressed by the 16-bit port address. So there in 85 we have used 8-bit addresses. Here we are using 16-bit addresses. Fine. So that 16-bit address we can represent it as direct and indirect. Fine. That we will discuss now, how we can address it, and then we can consider that input and output device as a memory also. So if we consider that as a memory, we are supposed to use 20-bit addresses, because 8086 is having 20-bit address lines. Fine. So if we consider this input and output device as a memory, we are supposed to use 20-bit addresses. Okay, fine. So that we will see now. Okay. So this is your processor, 8086 microprocessor, and this is your I/O spaces, which is of 64 kilobyte. Okay. So this I/O spaces you can address by using 16-bit address or 20-bit address. Fine. So this 16-bit you can use as a direct or indirect. So direct in the sense, if this is an instruction, you can directly mention the port address. So PA is nothing but port address. Okay. So this is the instruction format. You have to mention the operation and then you have to mention the port address. If you are using the direct address directly in the instruction format, you have to mention the port address. So if you are using an indirect addressing, then you have to use the DX register. This DX register will contain the I/O address. So which is nothing but the port address. So for example, if I would say if the port address is 2500, then if I use direct, I will write in 2500. Okay. If it is an indirect case, I will use in DX. So this DX register will contain the address line 2500. So this is how you can use direct and indirect. Okay. So when you receive one data, it has to happen through accumulator register. This we have seen already in 8085 microprocessor. You are supposed to use accumulator register to send, that means to transmit and receive data. Fine. The I/O RD bar and I/O write bar will determine the operation that you have to perform. So if you are performing a read operation, this line should be low. So then only you can perform read operation from the I/O device. So if you perform write operation, it should be I/O W bar should be 0 to perform write operation. Fine. So this is how the addresses of I/O devices are used in the 8086 microprocessor. So next we are going to see the modes of operation of 8086 microprocessor. Okay, so the 8086 microprocessor will operate in two modes. So one is minimum mode, another one is maximum mode. So this concept is not much bigger, it's just a simple thing. If a processor, a single processor, fine, if a single processor by itself is performing an operation, then that mode is called as minimum mode. So this minimum mode we will use for simple arithmetic or simple operations, fine. Then maximum mode is if more than one processor, fine, more than one processor, which means that more than one core unit, fine, is needed to perform an operation. At that time your processor has to adapt to the maximum mode, fine. So as a simple thing, minimum mode single processor will do all the functions. In maximum mode more than one processor is required to perform an function, fine. Okay, so before we will see about the minimum and the maximum mode, you should know about the pin diagram of 8086 microprocessor. So most of the pins you know already. I will just tell you the important pins that are needed for minimum and the maximum mode, fine. So this is the pin diagram of 8086 microprocessor. So here is your ground, VCC, ground, clock, reset, ready. So this you know already, and these are your address and data lines. Here is also there. Then NMI, non-maskable interrupt, interrupt request, interrupt acknowledgement, read, write. This you know already, fine. So to decide whether the processor operates in minimum mode or maximum mode, pin number 33 is used. If pin number 33 is 1, the processor is operating in minimum mode. If it is 0, which means the processor is operating in maximum mode, IM/M bar, fine. So in minimum mode, these pins are main thing. Hold acknowledgement, write bar, M/IO bar to decide whether I am performing IO operation or memory operation. DT/R bar, which determines data is transmitted or data is received. Then DEN is nothing but data enable, fine. So these are the lines, that means signals are used in minimum mode. Okay, so but in case of, okay, so these are all the pins that we use in minimum mode, but in case of maximum mode, some of the pins will be replaced with the other functions. So that we will see now. Okay, same 8086 microprocessor, all those pins are same, but from pin number 31 to 24, that means 21 to 34 is getting deferred, fine. So hold acknowledgement, write bar, IO/M bar, data enable, transmit, receive, all these pins are replaced with some other functions, fine. So request grant, these are request grant, this is lock, these are all the status lines, and these are all the queue status, okay. So all these pins are replaced with some other function. So this function is utilized only in the maximum mode and not in the minimum mode, fine. So request request pin and grant pin will perform the same operation as of hold and hold acknowledgement, fine. The pins replaced here will have the another name, but functions are same, similar, okay, quite similar. It's not a major difference between the pins functions. It's similar with some functions, fine. So now we will see about the minimum and the maximum mode, fine. So as I told you already, if a single processor performs its operation, then your processor should be in minimum mode. If more than one processor are attached to perform and function, that is maximum mode, fine. So in minimum mode, the control signals are generated with the status signals that are in the processor itself. But in case of maximum mode, you will require a separate hardware that is called as bus controller to generate the control signals. So what are control signals? Yes, to decide the operation that are performed by the processor. So whether it's performing memory read, memory write, IO read, IO write. So these signals are called as control signals. So to generate this control signal, we need a separate hardware called bus controller in case of maximum mode. So whereas in minimum mode we does not require such external hardware to perform this. Fine. So we will see the differences. So the first thing is, in minimum mode a single processor is required, no co-processor in the sense additional processors. Fine. No additional processors are required to perform the function in minimum mode, whereas in maximum mode multi-processor is required. Fine. So no such hardwares are required for generating the control signals, but here an external bus controller is responsible for generating the control signal. Okay. So minimum mode you can use for simple application, maximum mode you can use for complex applications. And then to decide the processor operating in the minimum mode, pin number 33 should be high. So that we have seen already. So this is a pin diagram, pin number 33. So if it is high means it is in the minimum mode, if it is low, 0 means it will operate in maximum mode. So if the pin number 33 is high, minimum mode, pin number 33 is grounded, which is nothing but 0. Processor will be in the maximum mode. So now we will see the architecture diagram of the processor when it is in the minimum mode, and the timing diagram of read and write cycle when it is in the minimum mode as well as in the maximum mode. Okay, so this is the minimum mode architecture of 8086 microprocessor. So here you have your microprocessor, this is your oscillator circuit, fine, and this is your memory, RAM, ROM, and then your IO devices, and this is a latch and transceiver, and this is a demultiplexer, fine. So this demultiplexer will generate the control signals whether you are performing memory read, memory write, IO read, IO write. So for this demultiplexer your input lines are IO/M bar, read bar, write bar. So this pin number 33 will decide whether the processor is in minimum or maximum. Minimum means I am supposed to give the value 1. So this pin is connected to the VCC, fine. Okay. So this is our latch, D latch, fine. So this D latch, okay. So this D latch will split the data lines and then address lines. So if we pass the address latch enable. So this D latch we will give the data and the address multiplex line as an input. With the help of address latch enable, we will split the address and the data line. This address latch enable is used to enable this D latch. Okay. So that's what given here. The AD0 to AD15. Okay. This is given as an input to this latch. Okay. Based on the address latch enable, my address lines and data lines, this is your data line, okay, D0 to D15, data lines are splitter. So here the data is stored in transceiver. So what's the purpose of transceiver? Transceiver will perform both transmission and reception of data, fine. Why the data is stored in transceiver? Yes, so when we are performing with an operation with an input and output device and with the memory, we will store the data in memory, we will get the data from the output device, we will send data to the input device. So to and fro, the data will be transmitted by the processor and the data will be received by the processor. So that's why the data is stored in the transceiver here, fine. Okay. So this is your address line and this is your data line that is stored in the transceiver, fine. So the data from the transceiver is given to the memories and the IO devices, fine. So when it will give is with the help of direction. So direction is determined by the dt/r bar. dt-r bar will decide whether the data is going to transmit or receive. Okay, based on this thing, the data, whether the data we will get from the output device or we will send the data to the devices. So that is decided by the dt/r bar. Okay. Then data enable signal will enable this transceiver IC. Unless this transceiver IC is enabled, we can't perform any transmission or reception of data operations, fine. And this is your RAM, ROM. So ROM is nothing but read only memory, where you can perform only read operation. So memory read signal only be connected. RAM, you can write and read data, so write and read operations are connected here. This is our IO device, so memory read, IO read, IO write you can perform. So CS is nothing but chip select. Fine. So this is what the architecture of the processor when you operate in minimum mode. No such complexities in minimum mode. Okay. So this minimum mode we will use only in the simple operations and not in the complex operations. Fine. So this is the read cycle of minimum mode timing diagram. Fine. So your clock signal, if we want to perform a read operation, obviously we need the address lines, then the data line. Okay. Initially you have to give the address values. Okay. A0 to A15, this is the lower and this is the higher. Okay, higher is 16 to 19. So to enable this, bus I enable value should be important. To demultiplex the data and the address lines, the address latch enable should be high. So that's why at T1 my address latch enable is high, so that the address values are split up from the data. So now we know the address. So processor now will look on to the address. So at T state 2 and 3 it will read the data. At that time read signal should be low. Now the processor move on to this location, read the value and put it in the data bus. At that time address latch enable should be low. Fine. So to get the data, we know that we are performing read operation to get the data, address latch enable should be low at that time. So at the read operation address latch enable is 0. Now we are receiving data. Okay. So we are performing read operation, no? So we are receiving data. So dt/r bar should be 0. So this read cycle will take 4 T state. In that 4 T state, dt/r bar data enable read signal should be low from T2 to T3 to read the data. Fine. And the address and the data lines are important, then address latch enable is important. Okay. The same timing diagram you can rewrite for the write operation. The only thing that two things will get differ. That is, instead of read you have to give write. Data enable is important, it will be same here. Here we are not receiving the data, we are transmitting the data, so this value should be 1. So I will show you the write cycle also now. So this is the write cycle for the minimum mode. Okay. So all those things are same, address latch enable, address, data. Instead of read you have to give write. So we know the address, we should know the data. Okay, that is placed in the data lines. So at this time your data should be enabled, and ETR we are performing transmission. Okay. So this should be high. So when this is high and read is low, data is enabled, the value in the data bus will be stored in the address that are given here. Fine. So this is the timing diagram of write cycle. Okay. Now we will see the maximum mode architecture. So this is the architecture for maximum mode 8086 microprocessor. So all the blocks will be same. Here you have your 86, oscillator circuit, transceiver, that is buffer, latch to separate address and data, your RAM, ROM, IO device. So all these things are same. The only difference is bus controller. So there in minimum mode we have used DMUX, but here a bus controller is used. The input for this bus controller is S0 bar, S1 bar, S2 bar, address latch enable, data enable, dt/r bar. So these control signals will generate the control signals: memory read, memory write, IO read, IO write. Okay. So the operations will be same, but here the operations will be same, the architecture is same. Two things are different. One thing is we are supposed to use more than one processor to perform the operations. With this processor we have to connect another processor to perform an operation. Okay. So why we are going for such thing co-processor concept in the sense, if you are performing a complex operation, if you want to interface more and more sensors and you want to collect more data to perform an application, that time you have to operate your 8086 microprocessor in the maximum mode. We have to attach a co-processor with it. Fine. Another difference is that to generate the control signals, you are in need of an extra hardware. Okay. So here we have need a bus controller. Fine. So this is the diagram of minimum mode and this is the diagram of maximum mode. Almost all the hardwares are same. The only difference is the bus control. Here we have used the DMUX, which is already in the architecture, but we are using a separate hardware to generate the control signals. Fine. So now we will see the memory read and write timing diagram of maximum mode. So this is the memory read timing diagram of maximum mode. So here also the same address slash enable higher address, higher address and data, dt slash r bar, data enable. So since we are performing memory read, this control signal is utilized. So memory read, so you are receiving, so this should be low and that time data should be enabled to read address lines, and then this is important. This is the difference between the minimum and the maximum. So this status signal should be active to get this memory read cycle. That is the difference, major difference. So all those signals enable and disable are same. The thing is status signal that will generate the memory read signal. That is important here. Okay. Okay, I'll show you the read cycle of minimum mode also. You can compare and now you can see. So this is for maximum and this is for minimum. All those signals are same. See here, all those signals are same. The concept is also same. The difference is the status signals. So this status signal will generate the memory read. Here memory read, that we already have a signal like that, then we have used. We don't require a separate hardware, no. So that's why here no such status signals are utilized, but here we have used a bus controller to generate the control signal. That is the difference here. Fine. So now we will see the memory write cycle for timing diagram of maximum mode. Okay, everything will be same. The difference is here you have to give write. Okay, write cycle. Here you are transmitting the data, so it should be high. Data should be enabled while you are performing write operation. Okay, so at the time you are performing write operation, data enable should be low. It should be high throughout the cycle, and you are performing write, memory write or IO write, depends on the operation. So TC is transmission. Fine. Okay. So that's the thing. Read and write a single in this regard. In the maximum mode, read and write is differed by the single signal. Fine. Okay. So as a summary, in this video lecture, we have seen about the physical memory organization, odd and even bank addressing, and then input output addressing capability, direct, indirect, memory mapped. Okay, fine. And then we have seen the modes of operation, minimum mode, maximum mode, and the timing diagram of read and write cycle of these two modes. Okay.